Maybe we should just look at that for a moment. See what I put there.
That is weird. Why is that upside down?
That's the way I feel.
Okay. Is that this toggle here?
So because some mountings you need to reverse it. Oops, installation.
Oh, somebody was using the scalars?
There you go. You got it.
Using a bar.
Okay.
Thank you.
So then what is it projecting?
Well, they might have
Yeah, so that they can turn the tablet around.
Engineering 101. I don't buy it, but anyway. Okay. Here's the final exam notice at the very bottom of the website page. Okay. I made a mistake about, I said problem 5.9 parts A and B, but I looked at this 5.9. Of course, it wasn't 5.9. It was the data was in 5.10. And also, the problem is a little bit messed up, so I gave explicit directions on how to do it. And I'll go over that now. The whole point is that there are 5 data problems here I want you to be familiar with so that you can answer questions on the final exam. As I said, you don't actually have to do anything coming into the final exam if you don't want to, but I think some familiarity would be wise. I'm going to be solving these problems on the final exam paper. Only I'm not going to give you everything. I'm going to make you fill in some of the calculations. So some of the calculations I would have done by machine, I'm going to make you do by hand. So I bring a calculator, a scientific calculator. You have to know how to do the calculations. If you know how to do them by machine, you might want to practice some of the calculations by hand if you haven't done that. But it's just calculations. If you ask it to multiply 2 numbers, you should be able to multiply 2 numbers. If you ask it to multiply 3 matrices, let's say small ones, you should be able to multiply 3 matrices. You'll see what I'm talking about if you actually do the problems, perhaps. I'm not going to ask you to invert any matrices, but I might actually ask you to multiply some matrices if they're small. And that could, you don't want to do that by hand because you're going to have nasty numbers, right? 4-digit numbers and junk, and you don't want to do that, okay, by hand. So show me your sub-calculations. That'll take 10 minutes or whatever with a calculator, but show me your sub-calculations and, go on with it. Just do it. Just show me what you would have done, okay? And I'll know that you know what you're doing. Whether you got the right answer or not, it doesn't matter, okay? As long as you show me you know what you're doing. So I'm going to ask you, basically, I'm going to do the problems for you, okay? But you have to know that you knew how I did them, okay? That's pretty much how it is. And then I'll ask you questions, and then interpretation, and so on and so forth. But it's going to be a lot like the quiz. That's what the quiz was. It was a smaller version of the same. I just gave you the answers to the problems. Okay? Only maybe not every. I'll leave some things out that you're supposed to then fill in. I might leave an F ratio out, or a p-value, or something. Hey, fill in this blank. Okay. Anyway, on 510, which is the problem, which is sort of the oddball problem, because we never got 511 really squared away. There's problem 510, which I'll read to you. It says, perform a thorough residual analysis of the data. Well, in fitting a multiple regression problem, what you have is, in problem 510, is that you have, you can't read this very well. My God, what is that? Is there also some kind of script on here that's not right? Is that possible?
Yeah,
oh, there it is. The cursor was on it. That was really messed up. What you have is you have 27 rows of data in problem 510, page 204. You'll see you have 3 x's, maybe you'll have to look at this data page. Can you zoom in on this page just for a second for those people who might not have their book with them if they're on a desert island somewhere? Okay, here's page page 204, problem 510. You have 27 rows of data there. What you have is you have 3 responses for each input vector x. For example, in the first row you have x1 equals -1, x2 equals -1, x3 equals -1. Then you have 3 y values. The y bar, which stands for the average of those 3 y values, and s sub I, which is the sample standard deviation of those 3 y's. Not the variance, but the standard deviation. That's conveniently given to you, so you don't have to compute it. On the other hand, you actually have to, well, somebody has to, fix this data up so that you can actually do multiple regression of the whole y vector, which is 81 long, 3 times 27, onto the 3 regressors. So what you have to do is actually add 54 rows, okay, to this assemblage, and that's what I've done. I actually did it in data for problem 510. Let's have a look at that. Just put that up there. I put it on the website, the data. So I put in, see here, the first -1, -1, -1 is repeated 3 times. And the 34, 10, 28, which was the first 3 y values, have been conveniently located in the column instead of in this row. I left the SI the way it was. But basically you're looking, these first 4 columns is what you need. You need to fit in part A the response y as a linear function of x1, x2, and x3. That's the multiple regression problem. And look at the residuals. Okay. See that they're not good in terms of the standard assumptions. I took the original data also and left it in this form because I wanted for I'm going to want in the later part B and C, I'm going to want SI as a function of x. Okay? I'm going to try to fit SI or some function of SI as a function of x. So transformation. Now what it turns out that is if you fit SI squared as a function of x, so then there's only 27 rows in the analysis now. There's no point in repeating the SI 3 times. Okay, because it's the same number. All right? So you're not really adding degrees of freedom, you're just adding junk. Okay? To your model. So if I fit the variance, let's say, it says fit the variances or something in part B. Use the sample variances as a basis for weighted least squares. Well, for one of the things, some of the sample variances are 0. I better look at that again. Let's have a look at that. So if the sample standard deviation is 0, the sample variance is 0. There's 1. You've got 3 repeated observations, all the same. Okay, and there's another one down there. Yeah, another 0. So what's that going to be? The variance, even if I didn't fit the variances, but I just used the raw variances as my weights. Okay, in other words, take SI squared, and 1 over SI squared is therefore the weight. Remember that? W equals 1 over SI squared. Oops, W equals 1 over SI squared. Okay, that's the formula for weight. Okay, even if I just use these, what am I going to do with 1 over 0? I mean, I could take a small number, but looks kind of silly. All right, so then with that in mind, say, okay, let's fit the variances SI squared to the weights. Just go up and use this column and add an SI squared column. You know, just square these SIs and fit those. Well, then you get negative weights. And you can't take a square root of a negative number because I have to take the square root of the weight in my weighted least squares approach. So that's no good. So I say, well, let's just skip part B then. Okay. And combine it with part C in essence. Vining and Meyer suggest fitting, Vining, which is the third author of this edition, suggests fitting the linear model to an appropriate transformation of the sample variances. Use such a model to develop appropriate weights, and then repeat part B. Okay, so part B is okay as long as you first estimate something else. And what I'm saying to do is take the square root of the standard deviation, in other words, the 4th root of the variance, and fit those to the x1, x2, x3. That's the transform. I'm just telling you to do it. Okay? Try it. That's what we're going to do. Okay? And you get something decent. Analyze the residuals analyze the residuals then of the weighted least square problem via residual versus predicted plot and normal probability plot, the usual two things you do. Okay? So we could go through some of that in a different problem. Maybe we'll do some weighted least squares today. Okay? So I don't want to go back to 511 though, because that's a messed up problem, I think. I didn't like that. The results never even came out very good when you took even the log transformation on the sample standard deviation. This is the same problem, only this one seems to work satisfactorily. Okay? It's the same problem as 511, only it works satisfactorily if you use the square root of the standard deviation. So the idea is to you have to introduce the weights, and there's an example of how that's done for a problem 511, just the results are unsatisfactory. What do you do? Anyone want to tell me? So what would the weights be? Let's just go ahead and regress. Let's just go ahead and regress. I'll just do this first part. I'll just go ahead and regress the square root of SI. Let's just do part of the problem. Okay? You can finish it up later. Okay? So let's do this. Let's regress. Let's take the square root of SI, right? So this number. Okay? And now I want to fit those as a function of a linear function of the x's. You can see if you try the variance, you should probably look at the variances anyway. Look at it. Maybe I should do both. Let's put in also a column for the variances and fit those. Let's just go ahead and fit the variances, the function itself, and the square root of it. Just all for fun. Okay? So you can see what happens. Okay, so those are the variances. So let's fit the variances as a linear function of the x's. Maybe give it a little bit more space so you can see what the variances look like. Okay, the variances are 0 and the square root of the... Well, all these zeros are still there. Okay? So if I took the log, for example, I'd get minus infinity. That wouldn't be too good either. So I got to sort of stick somewhere between a small power, a fractional power, and well, it looks like you'll see the higher powers are not going to work. Okay, so let's try that. Let's try the square. So let's go ahead and do the regression analysis tools. I'm going to want to get the residual output to see what the residuals look like. Y range, let's go ahead and put it in the variances then. Variances which are SI squared. Input X range, just the X's here. And only 27 rows, because I'm not working with the full data set, only with these sample variances. Labels, output range, residuals, output range. Just put it right here. Ah, no. Let's put it down over here.
This is with the variances, right?
This is for the variances. What overriding data is it going to do?
That little bear.
Oh, that little thing. Okay. Mess up all my columns. Okay. Oh well. Okay, so still can't read this one. Okay. So let's have a look. Let's just have a look at the graph. I don't even bother printing it out. I just want to have a look at it. What does the residual plot look like? Hey, where's my where's there another toolbar?
Probably just need to
Expand it to all the way.
Where's the toolbar insignia? Just come show me.
All right.
Far right?
There. Keep going, right there.
Oh.
Toolbar options. There. Somebody just...
Let's get them all on there. Okay. Okay. So there's the residuals from that fit. They look pretty crummy in terms of, they don't look, it's not that good of a fit. Okay. So, and the predicted are negative. That's not so good either. Okay. The predicted and the bad residuals. Okay, so let's have a look. I'm not going to mess with that. So let's go ahead and overwrite this thing again. Let's just do the same thing, only let's regress SI. Let's just say, okay, well, I'll take the square root of the variance. Let's regress SI onto the x's. All right. So now I'm just going to change this column, and then everything else will be the same. Okay. Yes. All right, now let's have a look. Now there's still a negative number in there for the predicted. Doesn't look as bad. But still, what am I going to do with that negative number? They gave it to us now. Okay, here are the residuals now. All right. Well, they're still not flat in some sense. Okay? So, one more time. And hopefully I won't get negative numbers. Okay? Now here are the residuals. Yeah, decent enough. Okay? I could, try another small power. Actually, there's a method for searching for a power called the Box-Cox method, but that's not worth it. Okay, it's a lot of computation, and we're just looking for a decent model. Okay? For the SIs. So then I'll estimate the square root of SI. So then to estimate then I'll have to what? Take the fourth power of that to get the estimate of the variance. Okay, and then take the reciprocal of that for my weight, then take the square root of that. So I'm going to take the reciprocal of the square of these predictions for my square root of weight. Well, you know how it goes. Weight is the reciprocal of the variance estimate. So I need a decent variance estimate. I've taken the fourth root of the variance and estimated it. And they're the predicted values. All positive now. And I don't have any zeros in there. Okay? So those are my fourth root of variance. Right? Is everybody following what I'm saying here? So what are my weights going to be now? So I can just copy and paste this column, and okay, this is going to be the variance to the one power. Edit, copy, paste it up over here. I guess I'm going to have to expand it a bit. Actually, I'm going to want to have the formula for it. That's what I'm going to want to do. Okay, because I want to pull it down with all 81 observations, right? Okay, so I want to take the formula. So I'm going to need some space here to make formulas. So let's insert a bunch of columns. That's not going to hurt anything. No, that's not going to help. I'm going to need all this data over here. Anyway, you know what you're supposed to do. You're supposed to take this data. I insert the columns here. Actually, here. So this is, I think, the easiest way to do it. See, I need one for W, I need one for each X, and I need one for Y. I need one for the thing before the W, too. So how many do I need? 2 more. All right, or I could do it all in one. But I'll just write the W, well, I'll write the formula for this fourth root of W, of the reciprocal of W. Anyway, let's put it this way. The variance to the 1/4, that's going to be my estimate, right? is what I've estimated. Have I not? And those are the formulas over there. So I just need equals. The first number in that block, what were the numbers? What were the references? They are R48, aren't they? Okay, R48. Of course, I want to freeze that. Plus, then obviously, R49, freeze, times X1, plus R50, freeze, times X2. Poor man's way to do computation. Plus R51, freeze, times, I mean, it's kind of clumsy, but it works. Okay? It's a nice calculator. Spreadsheet and calculator at once. Okay? And so that's my estimate of my 1/4 power of the variance. And I'm going to pull it down and get all 81 entries therefore. Okay? It's going to be repeated 3 times in each block. But since the data was conveniently given to you by yours truly, no problem, right?
And what was that formula?
I just pulled it off my regression that I just did.
Okay.
You see, I'm using the coefficients of the estimation are given here. I have the linear SI to the 1/2, or the variance to the 1/4, is given as a linear function of these these 3 variables: x1, x2, x3. So these are the coefficients of the linear function: intercept and the 3 slopes. I know it's not great, but at least they kept this estimate positive. Okay, and there's some variation in that, so we're happy. And now I have what? The weight, the square root of the weight, I guess, would be what? What's the square? If the weight is the reciprocal of the variance, then you have to unravel that. What's the square root of the weight? The square root of the weight is therefore 1 over the standard deviation, right? Square root of the weight is 1 over the standard deviation, which is 1 over the square of this number. 1 by the square of this number. Because the standard deviation is the square of this number. So the square root of the W, I don't bother writing the weight down. Okay? Square root of the weight is 1 by the square of this number. Okay. Okay. Now, I need to calculate. What do I regress on? What's the formula? I need to regress square root of W times Y and square root of W times 1, square root of W times X1, square root of W times X2, square root of W times X3. I get 4 columns. I need one more column here. Or do I? No, I don't. Yes, I do. I need the 1 also. Okay, so I need 4 columns for the 4 columns of X, of the X matrix. Only it's not X anymore. I might call it, I think in the previous lecture I call it a U matrix. So I need 4. I could get U0, U1. We could also call it a Z matrix, but we did that for the nonlinear regression. So just so you won't get too confused, I'll call it column U3, and then I'll have my new Y column. I guess we didn't even bless it with a name. Y prime maybe? I don't know. Can't remember what we called it. Okay. And so that's square root of W times I don't put the sign X1. And if you want to be able to read that later, you need
Shouldn't that be the ones column though?
yes, it should be times 1. I forgot to put in my ones column, so I'm going to have to do that. Actually, I don't. Yeah, I already have the square root of W, so I don't need that. You're right. So this is that's my U0. So I need to cut and paste this. You're right. Thank you very much. Okay, you're on the ball. Okay. So yeah. whatever. Okay, so I have extra column now. So I only did need that much. Okay, etc. Right? Now how am I going to do that? Well, what I'm going to do is I'm going to freeze the column number of the square root W, and then just pull this business across. Okay, equals this number, freeze this column only, times this number here. All right, that gives the job done. Okay. And so when I pull this across, I should get minus 0.3s all the way, and then plus 0.3 times 34. Okay. And then I can pull it all down, and I'll have all my U matrix sitting here, and my transformed Y's. Okay. Now I can regress Y prime on all 4 columns of the U matrix, no intercept. Because I have a n by 4 matrix in my linear model, but the first column is not all of ones. So Excel's automatic way to deal with a column of ones by just putting in the regressors, and then it adds a column of 1 automatically for its X matrix in its calculations. Won't be done. Okay, we want to go just use the no intercept calculation of Excel. All right. Remember, there's 2 modes: intercept and no intercept. And we want to use the no intercept mode, so we will just do regression somewhere. I'll just put it on a new worksheet so you can see what's going on. Regression. Okay. What do I want? I want this column for my Y's. Actually, I don't have a name in there now. That's too bad. Just pull these names down here. I don't know what to do. Yeah, just go with that one. No, I don't want to do that because then you'll be confused. Actually, I just pulled these 3 down because then everybody will be confused. I don't care because this is not returned in, right? See, my point is I want to get the labels in. Okay, so now I'll do it. And you can't put 2 rows of labels. Okay. I get my hard task, put all these in. Okay. Any comments about this? This is how you do weighted least squares. You got to get the weight somehow, by hook or by crook. Constant is 0 here, though we do have labels. New worksheet. Residuals we want. Okay, because I want to see how it did. And again, all this stuff. I hate all this stuff. I think we used it in 1 problem this semester. Okay. So here are the residuals. Well, there's the estimates and so on, and they're not so interesting maybe, except you might want to look at the standard errors. Remember, these actually do estimate the original betas. Okay? So everything, the betas in the original units, they don't have to be reinterpreted in weighted least squares. They're unbiased, and they have smaller variances than the unweighted least squares. So if we actually go back and study the unweighted least squares, we could compare the standard errors. Maybe we should do that. Okay? Get another sheet or put these side by side. We did do the original regression. Did I leave that on the first sheet? Over there? I think I did leave it, didn't I? Yeah, there it is. No, that was the other regression. Did I have another one? Did I do the original regression? Didn't I show you the residuals? Oh, I didn't. Oh, you're supposed to do that. Okay, well, let's do the original regression on the same sheet then. Make sure everything is kosher. Okay, let's data analysis to show you what's going on in weighted regression, to show you the theory of it. Okay, so let's do the unweighted regression of the y on the x's. This one, of course, I will need an intercept. Here I am doing the problem for you. You just have to go home and do it yourself. Okay, constant is not 0. Output. Residuals. Okay, so give me some place to put it. Let's put it down at the bottom here. Okay. So there are the coefficients. I need to see what the standard errors look like a little bit bigger. Okay, 12 and 15 for standard errors. Okay, the t-statistics are all big, but standard errors are 12 and 15, and you can sort of see these numbers, intercept 177 and so on and so forth. If I go over here to sheet 2, what does it look like? Standard errors are now 11 and 7. Okay? Okay, the estimates have changed, but that's just the way it goes, and they're still unbiased. Okay. It may seem strange that they changed that much, but they're still kind of in the ballpark. Okay? All right. The t-statistics are bigger, I believe. Some of them are, anyway, a little bit bigger. Okay? So better quality estimates. Okay? What do the residuals look like of the original non-weighted multiple regression? Okay, so the point is, what's the point of the weighted regression? You get smaller variances and also equal variances, supposedly. Okay, so if I actually plot these, which means that the estimators have the optimal properties. Okay, that's why we were doing it. We were trying to get the optimal properties. That's why the variances are smaller. So the whole point was to get to the smaller variances. Here are the residual plot for the unweighted regression. Ordinary least squares regression, obviously. Now it looks like there's some nonlinearity in the models besides the variances not being equal. But well, and then that's my kind of additional paragraph on the end of the web page. I say a little bit more. I say, well, okay, since you have lots of data here, you could actually fit some interactions or something like that. They're marginally or moderately important, but you can get away without them doing the weighted least squares. Okay, you can sort of get out of it. So let's go back here to sheet 2. Let's look at the residuals for the weighted least squares approach.
So is this another way to avoid trying to change it to a non-linear type of model?
No, it's not. If you really need the nonlinearity, you still really need the nonlinearity. But it's only moderately important in this problem. Okay, if I throw in the interactions, I think the t-statistics are all about 2. Okay. Here's what the weighted residuals look like. At least they're decent. Okay, they're not great, but you don't see a lot of nonlinearity there. Maybe a little bit. Okay, and there's an outlier or two, and you get the normal probability plots as well. They look okay. Okay, so that's it. You'll see this picture again. Okay, I guarantee it. Okay, that's it. Maybe you don't have to do this problem. Okay, study hard. Okay. Save the changes. Yes, go ahead. Save that. Okay? That's on the desktop only. All right, so as I pointed out here at the bottom, the following is not required but worthy of note. Since in 510 we have a full factorial experiment with replications, 81 observations, a little typo there, one may also fit interactions and more if you want to, but I just considered the following, the interactions, x1, x2, x2, x3, x1, x3. In addition to the linear terms, this may be done in both unweighted and weighted cases. Okay. So if you do it in the unweighted case, just the ordinary case, you get decent results. You actually get decent results. For the residuals, you might say, well, why even bother with this weighting business? Okay. Except for the fact that the variances obviously aren't equal. Okay, so what's going on there? Okay, you have this kind of contradictory information. If you actually throw in the interactions, it sort of clears everything up. All right, and so it takes care of the fact that the variances aren't equal. Weird. So I think it's actually, given the information, since the variances really don't seem to be equal, and there seems to be some kind of trend to them, okay, it would be better still to do the weighted case and then see how the interactions come out. Just go ahead, so you'd add a few more columns. The square root of w times x1, x2, square root of w times x1, x3, square root of w times x2, x3, and we did that too. It helps a little bit. I mean, it actually just shows more outliers. Okay, it flattens things out. So the residuals actually look really flat, except for about 3 outliers then. Okay. And it has only moderate need of the interaction terms. So, a simple, you might say, if I was going to do model fitting, maybe I'll just stick with this no interactions case for simplicity. But anyway, that's the problem. It actually came out halfway decently. Finally, gets the application of the weighted least squares. Any comments? Further comments about that? That's problem 510. Okay. Gratis. Okay. All right. So, again, I'll be asking you something about, theory. You have to know what that U matrix is, and all that stuff. What at least the right formula is. And you're going to have your books in case you get completely lost, but hopefully you won't be that lost. Okay? So, what are we going to do now? We still have a lecture and a half. Do you have questions for me? I have more notes, too. We're going to do a little bit more, but...
I just have a question on the homework for
yeah.
tomorrow.
And for tomorrow, also, there was a comment, there was at least, I got one email from Joe, and he said, well, what about part E of that problem? It seemed to be that's what he was asking about, because if you look at problem 9.4, is that what we're talking about?
9.4,
yeah. Yeah, 9.4. He was asking kind of about D and E, what do I do there? And if you kind of follow what's going on in the text, you might think, well, there's a lot of computation to do. They skipped an awful lot, didn't they? Of computation. Well, first, there's a couple things you have to do in the forward selection, backward selection, and stepwise selection. You have to input parameters. And I'm going to suggest officially, I didn't put it on the website yet, but maybe I will right after class, to use f in equals 3 and f out equals 3. That's probably the simplest one.
I use dynamic f in and f out today.
Okay.
Where you keep changing it with your degrees of freedom every time.
I didn't even know they had one. Okay. Did it work? What did,
I think so.
what did your dynamic f in, f out look like?
Well, that was kind of a question.
I didn't even see that. Where is that?
Well, it changed. You were changing the degrees of freedom every time you.
Yeah, you're changing the degrees of freedom, but okay. Oh, I see. So you're using 1 percentage point. So what are you using for your percentage point then? 15% or 20%? What alpha are you using then? That's your dynamic one. So you're picking one alpha and then using.
Oh, that's all regressions. It was C, right?
Yeah. So 9.4 suggestion.
Yeah, instead of, because they recommend just using a pitch 3, but they had using f of 0.05 and then 1, and then your I think it was n minus.
You need an F in and an F out for stepwise. Or an alternative is that he was using alpha equal 0.05 and then based it on the degrees of freedom.
Yeah.
Okay. And so the denominator degrees of freedom, it's always a 1 numerator degree of freedom.
Right.
And the denominator degrees of freedom has to do with how many variables are in the model. And in your case, I forgot how many the solar had in it.
Out every time, basically.
Yeah. And so what is F125 and 0.05?
125 was 4.24.
So you're just using something
from like 4.21 to 4.24.
Yeah, that's not going to make any difference.
Yeah.
So you used verse or alternatively. I would use something like alpha equal 0.10, okay, to be a little bit, you have to be a little bit less persnickety on these things to get anything usually decent. You don't want to force a variable out, when it's possibly going to be useful later. So I would use, alpha equal 0.10 if I was going to do that method. You could use alpha equal 0.05, that's fine. But for 0.10, you get something about 3. Okay, 1 in 25 gives you f equals 3, or 2.92. So anyway, alternatively, this is alpha about 0.10. Okay. Alternatively, alpha equals 0.05, you get f in. F in equals f out equals about 4.2. Okay. All right. So the dynamic thing doesn't, it has a very small effect, as you can see, unless you had a very, very small sample size and a whole bunch of variables.
And in the forward selection, do you just do it until you're done, or do you use an F in, F out on that?
Yes, you do. For forward, you have F in. Okay, let's go back and maybe we should look at the Hull cement data. Let's see, I think I have it right here.
Yeah, we actually have it on our notes.
Hull cement.
So, listen, see.
I guess I did my apps like that for all three. For the
Okay.
forward and
Yeah, you're okay. I mean, as long as you're, I can deal with it.
Well, I think why I was getting confused is this. The only place you talked about the F was once it went into stepwise when I was
Yeah, but you still do the same. Okay. Well, the thing is, you actually do an F in at the first stage, but you don't really see it. What are the F ratios? In other words, at the first step, I have 4 regressors in the Hull cement data. I have 4 regressors, x1 through x4. What are the F statistics for n? What are the F statistics? I would have to do 4 regressions, presumably, to get 4 t-values. All right? But actually, I can do those by hand, because I can say the t-stat for h beta equal to 0, all right, for the corresponding regressor, single regressor, all right? So for a single one regressor in the model. So let's consider all possible one regressor in the model. Which variable should I start with? And do I start with any of them? Let's go ahead and calculate all the t-statistics. Instead of doing 4 regressions, right? I don't want to do 4 regressions on each of the 4 variables. It's going to take me all night. So what I do is I actually calculate what are the t-statistics. What's the formula for in terms of the correlation? It's r times the square root of n minus 2 over the square root of 1 minus r squared. Remember that thing? Handy dandy formula? Okay. If you have simple linear regression, the formula is in simple linear regression, which is all I would be considering if I'm only going to consider one regressor, right? In simple linear regression, the formula for, and I have y equals beta 0 plus beta 1 x plus epsilon. Okay. If I now take the hypothesis that beta 1 is equal to 0, all right? What's the t-statistic? T-statistic can be written in terms of the correlation equals r times the square root of n minus 2 over the square root of 1 minus r squared, where r equals the correlation, sample correlation between y and x. Okay? So there's kind of a cheat to do all 4 regressions with the correlation table. So my first step I'm going to do with the correlation table. That saves me a bunch of paper, okay, if I'm going to print out all possible regressions. I'm just going to go ahead and calculate all these t-statistics at the first level. And so equals, this number, r, times square root, and I forgot how many numbers there were in this. In Hall? No. Not in the Hall cement data. We're in the Hall cement data. There's only 12 in this one. Okay, so this is a different data. This is the example 9-1.
Oh.
Square root 10 then, because it's 12 minus 2, which is 10, divided by square root 1 minus number squared. Okay, so this t statistics are as follows. Let's see if I got this right. If I square that number, this is the f. Then stat equals this number squared. How come I got different numbers here? I must have made different choices for my square roots. What did I say here? I got 22.8. It said h and I divided times 11. Oh, that's right, because there were 13 observations. Yeah, I made a mistake. Let's fix this thing. Square root of 11. Total was the corrected total. Come on. There we go. Oh, that didn't work, did it?
I think if you just go ahead and go down, and you just changed it, it'll change it.
Yeah, I messed that up. I'll have to go from here. Okay. Now it looks right. Okay? So those are the F statistics. So do they exceed 3? All of them exceed 3. Right? All of them exceed 4. So which one do I take? I take the variable that has the largest one. That's the forward rule. Okay?
All right. Somewhere in this.
Okay, that's the forward rule. So the best alternative would be to, if I start with, instead of x4, start with x2. It's got to be the best alternative starting subset model. Okay?
So I figure those F stats every time, right? Because
You figure the F stats for or T stats. You can just do T stats if you want, but then you have to. If you're using F equals 3, then you have to look at the square root of 3 for the T stat criteria. Okay? All you really have to do is look at the t-stats. So let's go ahead and do that. If I looked at these x4, here are the 3 outputs for, let's see, I can go ahead and look at them all now. So let's look at the first. There are only 4 regressors, so there are 2 regressor models following x4, right? x4, x1, x4, x2, and x4, x3. So I go ahead. I know that x4... well, then I'm only looking, therefore, for these the t statistics. There they are, the 10.4, the 0.4, and the -6. And when I square them, they're bigger than whatever my f in is. I continue. And so the biggest one is x1, so I add x1 next. Now, and x4 is still significant, so I don't drop it. But now let's go over to stepwise. Where well, that's in stepwise. Okay. Now let's go to the third step. In forward, you'll never drop anything. Okay, so far I've got x4 and x1 on the model. Okay. So now let's go to forward. Now how many subset models? I've got 2 in. I can only add, there's only 2 possible models now that I may consider. x4, x1, x2, and x4, x1, x3. Now, so I'm going to look at the t-statistic. x2 and x3, they're both significant according to my f in, let's say, is 4 even. Okay? 3 or 4. All right? We have to choose one. All right? That's fixed for the whole problem. So I take the one that has the largest t-statistic in absolute value. So I have x1, x4, x1, x2. Now with that model, though, now that I've chosen that, now I X this one off the map, so don't even look at it again, according to the automatic rules. All right? Now, however, with stepwise, the t-statistics for x4 has dropped too low in absolute value. So I kill it. I go back to the model x1, x2, so I have a totally different model now.
But for the forward, I would keep the x4.
Yes, you would.
That's where I was kind of.
Okay. And then you could still try to go forward one more time and look at the full model, which I don't know if I did anywhere here, and see if you could add x1, and I don't think you do. Okay, because it's not clear whether you could. Maybe you could add all 4 variables in the forward. Okay. Is that clear? Maybe it's not clear that you might be able to add also the last one. So you never drop anything in forward. That was a question now. Joe?
No, there's not a question.
Okay. Okay. So let's see. Did I do the all possible regressions? Here it is. Yeah. Did I do it? No, I didn't. What was I doing here? No. Oh, no, that's just the other piece of this analysis. Okay. Then I tried in stepwise though. Since in stepwise I could continue on. Believe me that you can't add x1, okay? And you get the full thing. But I could continue on stepwise. So I see if I can add. I have variable x3 and x4. x4 I wouldn't add because I've already seen that it wouldn't work. x1, x2, x4 from the previous analysis. Okay? So now I see if I can add x3, and I can't. So I'm looking through the model x1, x2 and the whole cement data. Comments about that? Okay, is that clear? I used f in equals 5 and f out equals 3 here. That was hard to get a variable in. But it still was possible to get x2 in there with that selection. Okay. Because 2.24 squared is it? Wait a second, it's not bigger than 5? Maybe I made a mistake. Yes, it is. It's bigger than 5. Okay, I made it as drastic as I could to explain that stepwise could get this one in. Okay, even with those parameters, 5 and 3, which is that's a tough. Those are pretty tough criteria. Okay, fairly easy to get out, but hard to get in. Okay, so that means you allow yourself. You can find really important variables. Okay. But I think it's not a bad choice. It just might not work for every data set that well. Okay? Questions or more comments about that then? Okay. What about backward? We didn't cover backward. Backward, you start with all 4 variables and see which one you drop out. So for that one, I would have to do the full model regression, right? So then you see which one you drop out first, and then you can probably go to one of these panels I've already done and figure out what goes next. So I won't have to recreate the wheel. So and you get to almost all possible regressions by going through these steps. There's a few that you've left out in the end, right? And actually here there's only 16 regressions, all possible regressions.
So in A and B, we don't really need to see the RB squared and CP and stuff until.
Well, okay, I didn't calculate those here. How do you calculate? So actually, each one of these, I'm going to go ahead and calculate CP. Maybe that would be a good thing to ask you on the exam. I'll give you a bunch. You have to calculate all that stuff. All right. What is CP here? Let's just go ahead and calculate it. What's a good place to put it? Right here, probably, because I'm going to use. Let's see. I need the full model sigma squared, so I can't calculate it yet. That's why it's not been done. So let's go ahead and get the full model sigma squared. I need to do a regression. So I didn't actually do the full model regression. I don't need the residuals. So let's just put it down here somewhere. Okay. So I need I need MS res full. Sigma hat squared right there. So let's remember what it is. It's D70. That's not too hard to forget. D70. All right? So if I want CP up here, and actually I won't be able to calculate CP easily for these one regressive model without some more formulas. I'll have to get the formula for SS res in terms of R, which can be done. Okay, I have to go back in my book and fiddle with it. Okay? What is it? SS? It can be done. Maybe I should skip it now. But for simple linear regression, I'd want to get everything in terms of the R, right? I know what SS R for simple linear regression. I know that SSR is beta 1 hat squared times S XX, I believe. Okay? Which is SXY squared over SXX. If you actually go, beta 1 is SXY over SXX. Okay, SXY over SX, and then I could bring that in terms of things. We know that R is SXY over the square root of SXX, square root of SYY. Okay, so by putting in and dividing by SX, so multiplying and dividing by SYY here, I get that this is equal to R squared times SYY. Okay, and so SS res is therefore equal to SYY minus SSR equals 1 minus R squared times SYY. Okay, I think that's what it comes out to be. Okay? Can you read over the cabinet? Okay. This is the definition of sample correlation coefficient. This is actually how SSR came out. You can read that up in your book. Okay, on about page 6. Okay? Or 7 or 16, or whatever it comes out to be. That's early on. Regression sum of squares. All right. Actually, they go to res first. They don't do regression sum of squares till later. Okay. Here's page 30. Oh. Yeah, page 234 has one of the formulas. Beta 1 hat was SXY over SXX. I remember that for sure. Okay, we've done that a million times. So, okay, this is correct. SYY is another version of SST, corrected total sum of squares. So actually I could compute SCP up here too. CP. Okay. Equals, I need the SST, but I could get that from any of these regressions. It's 2716. Okay? From all the regressions, say 2716 at the bottom, right? So this is equal to, what is CP? What is the definition of CP? CP is SS res P over sigma hat squared full minus n plus 2p. In the case of simple linear regression, p is 2. CP, this is p equals 2. And so I get 1 minus this correlation squared. There's something bad. Okay. Undo. Too late now, probably. Oh, no, it's not. Good. Thank you. All right. Sorry. H6. Okay. Okay. Times, I'll just copy in the 2716 for the SYY. Okay. Divided by D70. Freeze it. Okay. Minus n which is 13 in this problem, plus 2p is 4. Since we're
Is it supposed to be D70 or D79?
70. Thank you. Thanks for remembering. These are not very small. Okay. I assume those are correct. I maybe have made an error, but let's just see. If any of the other CPs are that big. Okay, so down here, what do the CPs look like? Some of them can be kind of big. What's CP? Over here, it's equals, you take SS res. Now P is equal to 3, right? Because we have 3 columns in the X matrix, 2 regressors and 1 intercept. So it's SS res divided by D70 minus 13 plus 6. And actually I should be able to check these were all possible regressions because this is example 9.1. They actually have all the CPs written down. So did I get my other formulas right? I got this one right. Okay.
It's on the sheet right there.
Yeah, it's on the sheet. CP, I have for, 202, 142, 315, and 138 for the other CPs. And those are exactly the same. Okay? Okay. 5.496 for this one. So is that enough calculation? You can calculate all the CPs then. X1, X2 had the minimum CP, I think. Okay. So you should be able to finish 9.4 if you haven't done so already. My comment about it was part E was to compare and contrast all the models. What the author did was compute the press residuals. Okay. You compare it based on the press statistics, which I'm not going to ask you to do after you've done all possible regressions. So part E, if you want to do that comparison of models using press residuals and so on, I'll just call it extra credit. Because you're going to get more than one candidate model, I believe. Depending on what you have here. Actually, it may only have one candidate model, in which case part E is moot anyway, depending on your parameters. So if you come up with 2 candidate models and you want to compare them, then go ahead. So you can pick your parameters if you want to, such that you will get the extra credit problem. All right? All right? Choose yourself more work if you didn't come out already. That's fine. I can deal with that. Giving extra credit. So is that going to clear this up? So is this a good time to take a break, you think? Maybe take it a little bit early? This is all possible regressions? Because what about, maybe we should make a couple comments about what the rest of the final exam is, and then we'll take a small break and come back and do one more new thing. Okay? So I think the final exam, let's put that back up here, was, let's see. So we've covered 9.4 and 5.10. Okay? 7.10 and 20. That's about splines and quadratic fits. I think 720 is kind of interesting because it goes back and asks, it's a good review problem. It's going to go back and ask you for prediction intervals and things like that. So that's one where I may say, okay, let's go ahead and do some calculation with your little old calculator. Okay? Do you know how to do prediction intervals? Okay? And if you didn't really learn it and you had to go look in the book, I'm pretty convinced you won't be able to get very far with that problem. So, if you could, great. All power to you. Okay? 8.5 is about, so in other words, you were saying, is the linear model or the quadratic model better? Well, you can look at the residuals and blah, blah, blah. Maybe you can't really tell from the graphs. Okay, but it says, okay, now construct some prediction intervals. Okay. Based on the 2 different models, which ones, give you the smaller intervals? Can you actually compare it? And it turns out you can in that problem. It's an easy comparison. 8.5 has to do with chapter 8. indicator variables. So it's like the lathe speed problem. Okay, lathe speed in tool life. There's something else that has to do with, that's kind of an interesting problem because it has to do with gasoline mileage. Does an automatic transmission or a manual transmission work better? Okay? Versus weight of the car. Yeah, it would depend on the, but actually if you just look at the mass of the car, you get some information just from the scatter diagram. And now you're supposed to do the analysis. Okay? And show me you know how to do indicator variables. And it basically amounts to the full model is just a linear spline with one knot. Okay? Linear one piece and linear the other piece. That's what the lathe speed problem was. So it's doing the problem you had on the midterm over, nice and streamlined. Okay? With chapter 8. 9.4, and then 12.8 was the nonlinear regression. We can go over that again a bit if you'd like. How we did that. If we don't do it today, we're going to do it again tomorrow. Okay? That's it. Let's take the break. And what else? I might throw more extra credit, but there's not going to be any other stuff, I think. You can throw an extra couple of grad problems or something, but at this point, since I've advertised it, this is it. Okay? For regular credit. Let's take a break.
Nonlinear regression notes.
Yes.